Yeah.
All right. Okay. Let's get started. I hope I can finish. Yeah, I hope I can finish fat characterization and start pH, titratable acidity. Let's see how far we can get today. All right. So what is the saponification value used for, Kristen?
To measure the level of fatty acid saturation.
Level of fatty acid saturation? That is the other one. The iodine value is measure of extent of saturation, right? Saponification value. Yes, Kristen. All right, you get it now.
Estimate the length of fatty acid chain.
All right, sounds good. All right, but I want you to remember something. When you state the definition of saponification or iodine or peroxide later on, put the unit. So the saponification value is milligrams of potassium hydroxide that saponifies 1 gram of fat. So, so that is unit. For iodine, it's grams of iodine picked up by 100 grams of fat or oil. Peroxide value we'll see later on is milliequivalent per kilogram. And free fatty acid is a percentage. So define those tests and provide the unit. Yes. The saponification value unit, it is milligrams of KOH that saponifies 1 gram of fat or oil. Okay. So now, if oil A has higher saponification value than B, oil B, which one has lower average fatty acid molecular weight? So think about it. B has lower. It's an inverse relationship. So a higher saponification value means lower molecular weight, because then in 1 gram you'll have moles. In 1 gram you'll have more moles of something that is shorter chain. In 1 gram of fat, you will have more of that molecules that have shorter chain. Okay, I lost you. All right, well, let's think about it together. It's an inverse relationship, remember that. So high means low, low means high. But how do you, so it is milligrams of KOH per 1 gram of fat or oil. So if you have higher milligrams of KOH, this means you have shorter chain. If it is shorter chain fatty acid, then it has lower molecular weight. There is more number of moles in 1 gram of sample. With shorter chain, you will have more moles, more molecules to get you to the 1 gram of sample. If it's large chain, less moles per 1 gram. If less moles per 1 gram, you need less milligrams of KOH. That makes sense? The shorter the change, you need more of it to get to 1 gram. The larger the change, less of it to get to 1 gram. Just think about it now. To remember inverse, just remember inverse. Inversely proportional, larger value, lower molecular weight. Also, remember the equation. So here's the equation. That's what we solved last time. You can take a picture of it if you wish. but it's molecular weight of triglycerides. So in the denominator, you have the 190. That is the saponification value in the denominator. So it's inversely proportional. Yeah, if you want, this is what we solved at the end of lecture last night. Okay, which test is used when testing the efficiency of hydrogenation? So hydrogenation is taking unsaturated oil and hydrogenating it to break double bonds to get hydrogenated oil. So what test do you do to test the efficiency of that? The iodine value, because iodine value is a measure of degree of unsaturation. So you would normally measure it at the beginning before you do the hydrogenation, and at the end to determine if hydrogenation was complete. Presence of free fatty acid is an indication of what? In your oil. If you have free fatty acid, what does that mean? You have high fatty acid, free fatty acid. Not necessarily. What does that mean? Talk about several things. All right, so we have an answer. I think. Let's see. Yes, Haley, that means we didn't do good job refining, or we didn't refine, because refining of the oil is getting rid of free fatty acid. You'll see in lab when we do extra virgin olive oil versus refined olive oil. In the extra virgin olive oil, you have higher percentage of free fatty acid. That's one thing. What else? What it indicates hydrolytic density. And hydrolytic density could be due to lipase and enzyme activity, or an example of frying oil. You put your potato, high moisture, high temperature, you break triglycerides and fatty acid. Okay, so it tells you a lot of different things. It depends on what you're looking for. All right, name a few physical characterization tests. Sunili. Melting point is one. What else? What did we talk about? We talked about refractive index. We talked about smoke point, flash point, fire point. Okay. Question, yes. Viscosity of the oil? Well, viscosity of the oil, it depends on temperature. So if you have different temperature, your oil will get more viscous. If you have higher temperature, it will get less viscous. But it's not something that you would measure to characterize your oil. Right? Okay. Got that. All right, so free fatty acids. So let's talk a little bit. We just said what we measure. We measure, it's a percentage. So it's like titratable acidity, and we will talk about titratable acidity next. So measuring the total acid. And free fatty acids is an acid. Fatty acids are acids. So we usually titrate with a base to get the percent, which is grams in 100 grams or grams in 100 milliliter. So it depends. If we weigh the samples, it would be grams per 100 grams. Okay, so free fatty acids are liberated by hydrolysis of triglycerides. So usually there are endogenous lipases in your sources of oil. So when they are not refined oil, you will have some free fatty acids in there due to hydrolytic breakdown of fats. It's an indication of refining, we just talked about, indication of hydrolytic acidity, indication of age of frying oil. So we just talked about all of that. So it is a simple assay. You're going to do it in the lab. You just titrate with a base. And normally we measure as oleic. percentage of oleic, but we can change that percentage of linoleic, for example. And that impacts the molecular weight of the fatty acid that we use in the equation. So again, the same equation that we derived multiple times now. So here you weigh your sample and then sample minus blank, the titration. So that means volume of NaOH that you needed to titrate the blank in the presence of phenolphthalein indicator. So you titrate to a pink color. Phenolphthalein in acid is colorless, phenolphthalein in base is pink. So you titrate to pink color and you run a blank, and usually the blank should be 0 or close to 0, and then sample minus blank in milliliter. You want to convert to liter unit, so you divide by 1,000. Normality is moles per liter, so you can cancel liters. 282 is grams per mole, so now you cancel the mole, and then you divide by the weight of the sample, grams to grams, and multiply by 100. It's a percentage. Okay, so if you calculate it based on oleic acid, then there are conversion factors for different dominant fatty acids. So if it's palmitic, you multiply by a factor of 2.19. So usually there is a table that is given to you based on the oil that you're using. Usually you use the highest dominant or the most dominant oil, fatty acid in that oil. Okay. Okay. Peroxide value. Peroxides are primary oxidation products. So they are, when a fat or fatty acid is oxidized, you generate a peroxide. And as the fatty acid or as oxidation progresses, peroxides convert to secondary metabolites, like aldehydes, for example. So this assay that you're going to do in the lab, it measures the current state. You take the oil from the bottle and you measure the primary oxidation product as is. Depending on when you buy the oil, you might have oxidation or not yet. It's the very fresh oil should be a very low value. So peroxide value then measure peroxides, which are primary oxidation products, and it's defined as milli-equivalent of peroxides per kilogram of sample. That's the unit, milli-equivalent per kilogram. So what you if you have peroxide in your sample, you add potassium iodide, it will react with the peroxide, it will give you iodine. You add starch as an indicator, the color is blue. You titrate with sodium thiosulfate to clear. So at equilibrium, milli-equivalent equal to milli-equivalent. Milli-equivalent of iodine equal milli-equivalent of sodium thiosulfate. However, here it's in milli-equivalent, so which is milli-equivalent, just to let me remind you, at equilibrium, right, milli-equivalent of one reactant equal milli-equivalent. If it's in milli-equivalent, then you keep the volume in milliliter, you don't convert to liters. And milli-equivalent or equivalence equal normality times volume or molarity times volume. So this equation is then simple. Volume times the normality. And it's sample minus blank in this case, because if you don't have peroxide, your blank should be 0 or close to 0. In your sample, if you have peroxide, then the titration for sample will be greater than the titration for blank. And this is the normality of sodium thiosulfate. You divide by the weight of the sample and you multiply by 1,000 because it's in 1 kilogram. That means 1,000 grams. And here you don't convert milliliter to liter because it's milli equivalent. So there is no multiplication by 1,000 in the denominator. Okay, so this stays in milliliter, and this is normality. You divide by the weight of the sample, you multiply by 1,000 because it's in kilogram, which is 1,000 grams. All right, any question? Oh. There might have been one in the chat. Oh. What anyway? Oh, to mix with the oil. For which the NOH, is it for percent fatty acids? We don't add anything. You just add the NOH directly in the oil and oil sample. I don't remember what did you guys do today, Mitchell? Did you add anything? You just had the oil and you titrated? Who did peroxide today in lab? Yeah, or not peroxide, fatty acid. Do you remember? Who did fatty acid? Okay, Molly. You weighed the oil and then you added ethanol. Okay. So we added ethanol to kind of get the oil to mix well, and then we added the indicator, then we titrated with NUH. Okay, thank you, Molly. Is that good, Rob? Hopefully. KI2. You gotta come to lab and then you will see all the reagents that we add. I don't have them memorized. We just make sure that the oil is mixed well, and then we can add the reagents. Okay, that's why we have labs. All right. All right, so another measure of oxidation present state is anisidine value and Totox value. You might have heard of those. These are very common for measuring oxidation. So anisidine value reacts with aldehydes. Aldehydes are secondary oxidation products. And then these aldehydes that react with anisidine will give you a chromogen that we measure absorbance at 350. Then you can take that value, anisidine value, and the peroxide value, and you can calculate Totox value. This is more better measure than just measuring peroxide or just measuring anisidine, because it gives you the state of primary and secondary oxidation. Totox is the anisidine value and plus twice the peroxide value. This is how it is calculated. And it gives you a kind of a picture of primary and secondary oxidation. And this is an example of fresh oil, soybean in specific. What would the expected value for anisidine and Totox be? Okay. Hexanol, or measuring what we call volatile organic compounds. A lot of the secondary metabolites of lipid oxidation are volatiles. So pentanol, hexanol, these are few of many that are volatiles. So you have alcohols, you have aldehydes, you have a lot of, like, a wide range of volatile organic compounds that are related to secondary oxidation products. Hexanol is usually the dominant secondary oxidation product in oxidized lipid. So measuring extent of hexanol in a sample usually is good indicator of secondary oxidation and correlates well with sensory evaluation. the positive thing about it is you don't need lipid extraction. So if you're measuring secondary oxidation or lipid oxidation in flour, oat flour has 7% fat. So it can oxidize easily over time unless the company that produces the flour heat the oats to inactivate enzymes. So, and they measure that treatment of the oil with respect to the stability of that oxidation or lipid oxidation. Stability of the oil against lipid oxidation. So if you have the flour, you don't need to get the oil out to measure hexamer. You can put it in a container and then you measure the headspace. That means you, after you let it equilibrate in a container, you get your syringe and take a little bit of the volatile environment above the sample in your tube, and then inject it directly to the GC, which makes it very, very easy method to do. No sample prep. As long as you equilibrate the sample and allow those volatiles to be in the head space. The head space is the space above the sample within a tube. Closed tube. Okay. Question? All right. Thiobarbituric acid reactive substances, or in simple way of saying that test that is not a full mouth, is T-bars test. Thiobarbituric acid reactive substances, T-bars. This is a common test for measuring secondary metabolites of oxidation as well, especially malonylaldehyde. Malonylaldehyde is a product specific from linolenic acid. So if you have oils high in linolenic acid, this is a good test for it. If you have very low linolenic acid in your sample, and mostly it's oleic or mostly oleic and linoleic, that's not a good test because then you won't have sufficient amount of malonylaldehyde produced during oxidation. So malonylaldehyde reacts with thiobarbituric acid to give you a colored compound. It correlates well with sensory, but sometimes it's not very accurate. Malonylaldehyde reacts with a lot of different, potentially different components within the assay. So it's best to do HPLC analysis of the aldehydes. It's commonly used for meat products. So you have many options. You just go with whatever would be most accurate for the type of sample you have. Okay. Now, this last piece I have is measuring oxidative stability over time. So what we talked about is the current state of oxidation. You get a sample, oil, fat, and you measure peroxide, you measure T-bars, you measure hexamer. You're measuring the current state of the oil. But often you want to determine the stability of your oil sample, especially if you're testing a natural antioxidant, let's say that you want to add, or as compared to a synthetic antioxidant. So you want to determine the time until your oil starts to get rancid. So we call that time induction period. Induction period, what? It died. The battery died. No, it didn't. Okay, induction period. So you store your oil. You can do accelerated shelf life testing. You can do it at room temperature over weeks or months, or you can do it accelerated so that you quickly get an answer. And then you measure lipid oxidation over time. And you determine from time 0 to X time where you start detecting oxidation product. From time 0 to the time when you start detecting oxidation product is called induction period. All right, so that's the time to get to a value for oxidation. So often we do accelerated shelf life tests. So because we don't want to wait weeks and months to determine the stability. So we determine induction period using accelerated shelf life. So I did update your slides because I added 3 slides. So I did update those slides on Canvas today because after this I added 3 slides. Anyway, I talked about the oven storage test in one slide, oil stability, and oxygen pump. There are 3 different ways of measuring the induction period. So what you do is you abuse the oil under these 3 different ways of abusing the oil. And every certain time point, you measure lipid oxidation. Oftentimes, people measure peroxide, especially if you're starting with really very, very fresh oil. Oh, did I skip a question that I had? I think I did. I just remembered. Peroxide value of 0, what does it mean?
Freshly refined or fresh fruits?
Fresh, not freshly refined, but just a fresh oil that no oxidation happened. But also a peroxide value of 0 means what? Peroxide is primary oxidation, which will convert later on to secondary oxidation. So it could be a very, very rancid oil. How do you know? You just smell it. If you measure peroxide and it's 0 and you smell the oil like this, no, it is very, very, and that's what you're going to do in the lab. You're actually going to plot peroxide. I don't know, Rachel, sorry. Please, I have no idea why they don't update, put new ones. Ah, there we go. So we plot peroxide value over time. And if you have really, really fresh oil, you start at very low peroxide value, and over time at high temperature, what's going to happen? You're going to increase the peroxide value, and then you reach a maximum because you run out of fatty acids that can be oxidized. You oxidize all potential double bonds. And then what's going to happen after this with the peroxide value, with more time? It's going to go down. And then you reach to no more peroxide value. So here you have the rate of peroxide generated higher than the rate of this. So we see an increase. This is converting primary to secondary oxidation product. But on the other end, you have the rate of conversion of primary to secondary higher than the rate of converting fatty acid into peroxides. You reach to a point that there's no more fatty acids to be oxidized or no more double bonds to be oxidized. So all the peroxides in your sample will be converted to secondary. So you have a very fresh oil, very rancid. Very fresh. Typically, you start with very fresh oil and you monitor peroxide formation. And then by just smelling it, you know that the peroxide value of 0 could be here or could be here. Could be very fresh or very rancid. Okay. So in this case, we are measuring the induction period, very fresh oil. We are having an experiment with antioxidant or just comparing different oils to each other. We abuse the sample if we want to do accelerate. So oven storage is simple. You take that oil and you store in an oven at 60 degrees C. And periodically take samples out over a span of time. Sometimes it is 3 weeks, sometimes it's 6 weeks, depending on the oil level. And then you measure the time until you get a quantitative value for peroxide. That's the oven storage test. The other one is oil stability index. So here, it's a quicker test. You have automated equipment, Rancimat. What happens is you put your sample in a flask, closed flask with an opening to bubble in oil and another opening to allow volatiles, acidic volatiles due to oxidation, to escape and go into a water trap. Then you measure the conductivity of that water flask. So you want to imagine something like this. So you have a flask with your oil in it, and then you have a fork or whatever, something that you have a tube here and tube there. So here you're bubbling in air, here formic acid is coming out, and then it goes into a water trap, H2O, then you measure conductivity. So this oil is placed at really high temperature, 110 to 130 degrees. So there are oil baths because, you know, water doesn't heat up above 100, it evaporates. But instead of a water bath, oil bath, and then you can heat it up higher to 100 degrees. Okay. Last one is oxygen bomb. And literally it's a bomb. But how does it function is it really measures the drop off pressure. So you take a chamber, you put your oil in it, you pressurize that chamber by oxygen, and you heat it up. You heat up that chamber at really high temperature, 200 degrees C, and then you monitor drop in pressure or a sharp drop in pressure because of oxygen uptake during oxidation. Oxygen will be taken up, and then we have a sharp drop in pressure. These are the 3 different methods. The most common and the easiest is the oven test. Okay. Any questions? So well, I lied. This is the last bit. Okay, so characterizing the different lipid fractions. So we said for the nutrition label, we need the total fat, yes, but we need trans fat, we need polyunsaturated and saturated fat, we need cholesterol. So sometimes we want to know, not for the nutrition label, but in general, we want to know how much phospholipids we have, monodiacylglycerol. So fatty acids, we measure them usually the way you did in the lab, but we would run a calibration curve for every fatty acid. So what you did in the lab was semi-quantitative. To do the complete quantification, we'll run standards, calibrations, and then determine fatty acid composition. Monodi and triacylglycerol, we can run by normal phase HPLC. Same with phospholipids. Cholesterol, we can do GC analysis. I'll show you on the next slide. And then we can determine pigments and vitamins by HPLC as well. So we can do GC and MS analysis. We can also do thin layer chromatography if we're doing qualitative. So fatty acid, like I said, by the same method that you did in the lab, but the difference would be running standards for every fatty acid. And the cholesterol, in a sample, you want to saponify everything. Cholesterol is not an ester, so basically your triglycerides are saponified and removed from the sample. And then, like you saponified in your FAME method. And then the residual component, which is cholesterol, is not saponifiable matter. You derivatize by the trimethyl 2-trimethyl silyl. This is the GC component to measure by GC. So you make it volatile and thermally stable, so you can measure it by GC. This is the qualitative. Those of you that did experimental nutrition or are doing experimental nutrition next semester, you will probably do that from blood samples to look at the distribution of lipid fractions. But it's also done in foods to look at the qualitative distribution of phospholipid, monoacylglycerol, diacylglycerol, free fatty acid, and triacylglycerol sample. So you run standards, your sample, and another sample. So it's qualitative, basically. And that's it for fat characterization. Questions? So we'll start the remaining 15 minutes or so. We'll start the next. pH and titrated acid. So completely different something. Okay. I think when we talked about buffer, we had that similar question. So see if you can remember. Food organic acids, are they weak acids or really strong acids? So if you compare organic acids like lactic acid, like malic acid, tartaric acid, what other acids are there in foods? Citric acid, and there's also acetic acid. Yeah, compared to H2SO4, HCl, huh? They're weak acids. Thank you. So they're very weak acids. Because they're weak acids, they have a good buffering capacity. They don't fully dissociate. So remember the dissociation we talked about earlier for buffers. So you have HA, and then you have A minus. What are these? Do you remember what they're called? So let's try to remember what they're called. What's HA? And which is acid, which is base? Tell me. Yeah. So this is the acid, and this is conjugate base, we call it. In the world of buffer, conjugate base. In other words, associated acid, dissociated. Because this have the H associated to it, the A minus have dissociated. Okay. All right, so they have good buffering capacity because when they are weak, at any time point, they're not fully dissociated. So if we titrate with an acid, the conjugate base is going to pick up a proton and level up the pH. If we titrate with a base, the HA is going to give up a proton and level up the pH. And can buffer at multiple pHs. That is true. Why? Organic acids have carboxyl groups. organic acid has COOH. Some organic acid have one COOH, other have three, other have two. Okay, so when you have multiple COOH, you have different dissociation factors. So when you have different dissociation factors, the acid can buffer at multiple pHs. And we'll give later on examples of different organic acid with different number of carboxylic group. Acetic acid versus vitamin C, or ascorbic acid versus malic acid, 1, 2, or 3. Okay. Not in that order, but we'll show you later. So these organic acids, if they have more than one COH, they have multiple dissociation factors, therefore they buffer at multiple pH. Okay. So it is all of them, the answer to this.
Take the chat.
The chat, we have a chat. Thank you for keeping track of that. Wow. D, yes, all of the above. Rob, all of the above. Yeah, okay. Next. So 2 drinks with the same pH have the same titratable acidity, but different sourness intensity. Think about it for a minute. 2 drinks, they have the same pH. Would they have the same titratable acidity, but different sourness intensity? There's so many things wrong in this sentence. Let me tell you, it's false. Yeah. Like when you drink something, it's too sour. Or 2 drinks, one is more sour than the other. Right? Oh, well, it's the same person, not multiple people. Have 2 drinks in front of them. They're going to be able to tell the difference in sourness between. But others might give it a sourness of 10, you might give it a sourness of 15. It doesn't matter. But if you have the same 2 drinks, you will be able to pick which one is more sour. So if what I'm asking you, is sourness associated with percent acidity or with? What's the answer? But is it correct? Who agrees with Varvani? Who says titratable acidity relates to sour, total acid. But the sourness does not directly relate to pH. Of course, lower pH will be more sour, but depending on the acid you have in the system, sometimes to reach a particular pH of 3, you need to dump in a lot of acid. Other times, one particular acid will get quickly pH 3 with less amount of acid. So the amount of acid correlates stronger with sourness than the pH itself. And that is because of the dissociation and the strength of that acid you have in the system. So it's false. Okay. What happened? Gray, what happened? Did I confuse you?
No.
There is a question. Thank you for being the Zoom link. Oh, there's 3. Why? True. Gang. Why is it gang? This is false. Okay. All right. Appreciate the participation, you guys. All right.
No.
All right. So titratable acidity measures the total acid concentration. So it's total acidity and it affects the flavor more than the actual pH. Okay, so total acid. So I'll give you an example, maybe will resonate with you better. So proteins are buffered, right? They are buffered because they have carboxyl groups and they have amine groups, so they act like buffer. So if I want to produce a beverage at pH 3.4, which is common pH for acidic fruity beverages that you find in the market. If I want to prepare 2% protein beverage and 5% protein beverage and reach a pH of 3.4 in both cases, I'm going to ask you, tell me.
Why me?
Because you look so dumb. It's not, I need to talk to me. Okay. All right.
No, go ahead. Ask your question.
2% protein, 5% protein, and in both cases, I want to reach a 3.4 pH. Which one I need to dump more acid in to reach to the 3? The 5% protein or the 2%? Yeah, because he was not with me 5 minutes ago. It's okay. It's not your day. It's because proteins are buffered. So they're gonna buffer the pH. I need to dump in more acid to reach down to that point. So the 5% protein beverage would require more acid, and that's the problem with high protein beverages that are fruity and flavored. These are the ones that will be more sour, more acidic. So that is the problem with these beverages. Okay, so hopefully this resonates a little better. Okay. So pH, we measure the free hydrogen ions, so the dissociated hydrogen ion. So in water, so water is H2O, right? So the water, it breaks down to hydronium ion and hydroxyl ions. So hydronium ion, basically your H2O picked up a proton, or your H2O lost the proton. When we measure pH, we are measuring the concentration of the hydronium ion, okay? The higher the hydronium ion, the lower is the pH. The higher concentration of hydronium ion, the lower is the pH. So we'll show you this in a little bit. Okay. So before I let you go, pH impacts what reactions in food? Why pH is important? What does it impact? It does impact the color. So what changes in color, are they chemical reactions? Are they enzymatic? So changes in color of especially phytochemicals at different pH will have different color. So chemical reactions. So pH impacts chemical reactions. Yeah, that's a chemical reaction. Yes. But other than chemical reaction, microbial growth. That's why pasteurization in acidic food less than 4.6, we pasteurize at lower temperature. Because pathogens get killed at lower temperature under acidic conditions. What other? There's one more. Thank you, Griffin. Yes, enzymatic. Every enzyme has optimal pH. So in food, pH is very important because it impacts enzymatic, chemical, and microbial growth. All right, guys, I'll let you. We'll continue on Wednesday. Do you want a chocolate to wake up? You can come to my office. Great.
Need more than that.
Okay. All right. Are we good? Is there anybody here?
Yeah.
Thank you, Jordan. All right.
Oh. And then I was like. I don't know, man. Wow, I think everything doesn't get it right at the minute.